Assalamualaikum warahmatullahi wabarakatuh and a very good morning. So today we are going to do XPS workshop. So I already shared to all of you step by step for XPS fitting workshop. So basically for XPS, what we're going to do is first we want to know the objective when we run the analysis of XPS. So X-ray photoelectron spectroscopy, widely known as XPS, is a technique for analyzing a material surface chemistry. For a layman, actually, when you are dealing with metal oxide, so XPS is very important whether you want to confirm the presence of metal oxide. So we know that one of the properties of transition metal oxide, they have multiple oxidation state. So from XPS, actually you can determine the oxidation state, I mean the specific oxidation state for your material. So this is a CASA software to analyze the XPS. So what you need to do, first thing, go to file and click open. So you can open your file. So XPS data normally come up with a .vms. So like this one, VMS. So it's come up with VMS file. So either you can get this VMS file or you can only get the Excel file. So only get two. If you only get the Excel file, you can only do the XPS fitting using the origin. So if you get the VMS data, you can use CASA XPS to analyze your data. So just click open your file. So the software will directly open, and first thing first, it will go to the survey spectrum. So what you will see from the survey spectrum actually is a bunch of peak, but you didn't know what peak it is. So the first step, what you need to do, click on your graph and click the library. You can see the library icon on the top, or you can press F10 in your laptop or computer. So click the library. So basically you can actually randomly just know what actually the peaks belongs to. For example, your material contain metal oxide with oxygen. You can just click, for example, this intense peak, I want to know what is it. So when I double click on the peak, you can see randomly all the peaks that belong to that binding energy will appear in the XPS CASA library. So because my sample have oxygen, so here I know that these intense peaks belong to O1s. So again, you can use to identify other peak. For example, I click on this double peak, so I know that my metal oxide, which is cobalt, is present, and this might belong to the cobalt oxide. So this is just randomly. And one more thing, if you want to guess overall in your compound, you already know. For example, you know that you have nickel cobalt phosphate, you have a MaxSyn or whatever. So first, what you need to do, clear all the element and click the predict table, the second tab. So what here, so you know it, you can actually manually insert the element present in your compound, but you can click here, find peak. Then the software will find every peak that belong to that binding energy, but you need to eliminate some. For example, you don't have sodium in your compound, strontium, you don't have GD, you don't have aluminum, silicons, and also you don't have boron and also chlorine. So here you have additional titanium because of the MaxSyn. So based on this result, they will identify all of the peaks present in the survey spectrum. So they will scan whether all the peaks present or not. So next, what you need to do, create a region. So they will create a region, and you want to have this, normally this icon will not appear, but already appear. Actually, you can make it appear from the F9, which is annotation. Click the annotation here. We did it first. So first, the annotation, you need to go to the peak label and component, because you label for component, and click apply. So, oh, excuse me, it's not a component. Before that, go to the region, click region and click apply. So all the peaks that you already create a region will come out here. So you know your sample will have O1S, C1S, F1S, CO2P, Ni2P, P2P, and Ti2P. So if you know your exact compound or composite, you can directly know from the survey spectrum. Okay, that's about the survey spectrum. Okay, next let's do one by one. Let's do individual peaks. For example, we're choosing oxygen. So oxygen is easy because O1S. Okay, if I am a layman, a new with XPS, when I see this, this might only have one pix. If I'm a little bit expert, I say that you have actually another pix here. But actually, if you study XPS, first what you need to do is you must find actually what peaks that connected with O. It might be C double bond O, it might be CO, TiO, or whatever that belong to your sample. You must read some literature that know how many peaks that your oxygen O1S have their convolution. You want to know how many peaks. So without further ado, let's say that I already read the literature and I know exactly at which binding energy the peaks will appear. What I need to do, I click at the graph once, then click here, quantify F7 to create a background. Okay, first I create a region. This is the first step, which is region. Create the, so just click once. So here you see the background is not straight, so we want to have the straight background. Either you want straight or not, depend on you, but normally we would like to have a straight background. You can move this cursor, see, I can move until almost get the straight baseline. So after that I click the component. Components means that how many convolution peaks or deconvolution peaks your sample have for O1S. When I read the literature, I know that it has 4. So I must create 4 times 1, 2, 3, 4. So then if you know the position, so you know this is around 536, 535, 534, you can adjust the peaks, you can move the cursor. Okay, then in the end what you need to do is just fit the component. So when you fit the component, you can see only 3 peaks appear. So the red color means that this is beyond the range. So you can just highlight and click once and also cut. So you want to remove and create another one because you read the literature, it has 4 peaks. So you can move these peaks at the exact position that you want. Then click fix again. Then it has 4 peaks. So the main important things here, you must actually know which binding energy because you can still move the peak. For example, you read the literature, you know this is from 532, this one is from 530, and so on. And you must click fit the component. It is very important. And here what we call that the envelope, you should not exceed the envelope. Okay, you can see here this is too far from the envelope. Okay, this is over the envelope, we don't want that, so be careful with that. It is very important. Okay, so make sure to minimize the distance between your peaks and also the envelope, because the envelope will also be included in your analysis plot data using the origin. Okay, I think that's all. So what you need to do is next is you need to label. You can actually label which peak belong to which one. For example, this one is C double bond O. Click enter. For example, this one is C O C, enter. For example, this one is T I O C, enter. This is just randomly, you can refer to the literature. For example, this one might be due to COH, enter. So you can actually what we call that label the peaks, and then you can also save the data. So you click here, save the tab as key to clipboard. Click here and click save, and after that you can save as the text data. So I think that's all for our workshop. It's very easy. I hope all of you can what we call that, can do this analysis when you are dealing with metal oxide. And one more thing before we end, I share with you with online library how to use. You can go to srdata.nist and click for retrieve data for selected element. So when you click retrieve data for selected element, so here click binding energy and go to step 2. Then after that, here you have a lot of library here. So for example, you want to do for O, so oxygen, okay, click the oxygen, is O1s and click search. So here is all the library that you need to refer. For example, here you can click here to arrange the data ascending order. So you know that maybe if you sample, you have, for example, is a barium oxide, so your peak should be around 527 electron volt. So if you have plumbum oxide, it's around here 527. So it's all here. All you need is to refer either this data or from literature. So I think that's all for our CASA fitting XPS workshop. We will see in the next video. Okay, bye. Have a good day.